will show you how great I am. I wanna fly, can you take me far away? Give me a star to reach for, tell me what it takes, and I'll go so high, my feet won't touch the ground, this is my wings.
Wait, that wasn't coming from me, was it? No, it wasn't.
No, I think it was coming from Johanna. It's okay, don't worry. Hey guys, I was wondering, can you guys hear me by any chance?
Yep.
All right, perfect, thank you. It's 5:03, I think we're gonna start at 5:10, so we give the opportunity for everybody to come in. Yeah. Hey guys, I just have to send a few pictures to my iPad, so I'll take a few more minutes to do that, and then we'll start. All right, guys. So I think we're gonna start now. Welcome to the second workshop of the second statistics workshop. People are still coming at quarter past. Well, that's okay. Can you guys hear me loud and clear? I just want to make sure I'm not speaking into the wind. Hello?
Yep.
All good. All right. By the way, if you guys don't understand something, first of all, this is being recorded, so I'm gonna share my screen now. Start broadcast. All right, so this is being recorded. So a few people asked me to, there you go. A few people asked me to record the session because they couldn't attend because they're in different time zones. So that's what we're gonna do. Can you guys see my screen, by the way?
Yeah, we can.
Yes.
All right, perfect. All right, so just to give you a quick overview before I go in, we're gonna study quickly a few definitions on permutations and combinations, and one past midterm exercise that was really done badly last year, or a few years ago, and then a small review in conditional probability, and we got two more exercises for you guys. So we'll jump right into it. All right, so first part of the lecture, combinations and permutations. Have you guys seen that in class already by any chance, or no, not yet?
No.
No, right. Where are you guys at in class at this moment? I know John's really slow, but
Union and intersection.
union and intersection. All right, so that's what I did. Yeah. There's definitely stuff that I didn't mention in the first workshop. I think the theorem of total probability. Obviously this is not a substitute for class, but I hope that helps as support. All right, so first, so I got two definitions. The first one, definition 1, is combinations. Sorry for my handwriting. I know it's terrible, but whatever. Wait, in the red and white. All right, so the number of possible, two people in the waiting room, sorry. You admit all. I'm still not able to configure the thing in such a way that everybody gets admitted automatically, but whatever. All right, so the number of possible combinations of k items. So that would look k different items that are taken, essentially, that are chosen from a set of n objects. Well, actually n items. I'm gonna stay rigorous with my pronunciation. With n items. So you're essentially taking k items from a set of n items. So which implies that k has to be smaller or equal to n. You can't choose 6 items out of a set of 5. So k smaller or equal to n. So it's the number of distinct k sets. What I mean by k sets, by the way, is sets that contain k elements, because we're essentially taking different sets that contain k elements. So distinct sets of k that can be assembled. That can be assembled when order. This is extremely important. When order is not considered. So pretty weird definition. Just going to give you a small illustration. Very simple. Let's say I have 1, 2, 3, 4, 5, 6. So it's a it's a set of n equals 6 items. And let's say I want to select k equals 2. So the combinations by definition is how many different ways can I combine 2 elements from the set of 6 elements such that order is not considered. So we'll have 1, 2. So it's a set of 2 elements, k equals 2 elements that comes from the n equals 6, 1, 3, 1, 4, so forth. Now, the important aspect of that definition is ordered is not considered. Now, ordered not considered means that is equivalent to saying that guys, I'm sorry, I have to go back a few many times. 1, 2, for example, is actually the same as 2, 1. So I can actually, so when I take k equals 2 items, I can choose 1, 2, 1, 3, 1, 4. But I can also choose 4, 1, 4, 2, 4, 3. But notice that when we're dealing with combinations, 1, 4 and 4, 1 are considered exactly the same. So you would count that as one combination. All right. Does everybody understand that, the logic behind that? All right. I guess I don't want to feel like I'm talking too much in the wind. So it'd be great if if there's something that you guys don't understand, please speak up or anything of that sort. So second definition. Oh wait, no, sorry. There's just one little formula that I want to add. The way we note combinations. So Kn. So C for combinations, choosing K items from a set of N. Set of N items. And that is equal to, there's a formula for that, and it will be equal to N factorial divided by K factorial, N minus K factorial. Does anybody need a refresh on what factorials mean, or does everybody know what a factorial is? Or does anybody not know what a factorial is? So it'd be easy. All right. Nobody's complaining, so there you go. So that's for combinations. The second definition now. This is fairly elementary stuff. I'm sure you must have seen it probably in your high school stats class or math, whatever. So for permutations, so definition 2, permutations. All right. So the number of possible permutations.
Matsu,
What? Yes.
is
Sorry.
the formula above the equal to the number of combinations?
Yeah. So the formula above,
Okay.
N factorial, yeah, it's the number of combinations if you take K items from a set of N items, where
Okay.
K is smaller or equal than N. So the number of possible permutations now of K items. So again, it's same thing. It's a set, right? I have it right here. Set of K items chosen from a set of N items. So this implies that K again is smaller or equal to N. Otherwise, wouldn't make sense. So the number of possible permutations of K chosen from N is the number of distinct sets of K. I'm going to say length K. Don't really like that word, but okay. That can be assembled. That are assembled. And that's the other important part. That's what sort of differentiates permutations from combinations. When different orderings are actually considered or are considered to be different. So when we're looking at combinations, I said order is not considered, and I give you the example that 1 and 2, 2 and 1 is actually the same. So the ordering does not matter. It turns out that if you order 1, 2, or 2 and 1 the other way, it will still give you it's still considered one combination. The only difference with permutations now is that 1 and 2 and 2 and 1, that specific example. So i.e. if you have 1 and 2 and 2 and 1, these are not same. So that will equal to 2 permutations. And the thing is, depending on the exercise that you'll have, I'll just give you the formula first. So the way you could permutate K items from a larger set of N items is with this formula, N factorial over N minus K factorial. And notice that note that P K N is greater or equal than then combination Kn. It makes sense in the formula because well, we have a k on the bottom. K factorials are defined for positive integers, so that will make combinations smaller. And even intuitively, I gave the example right here. This is considered as one combination, and at the bottom, these are considered true permutations. So it must be that when we're permutating elements of a set, it will be larger than the combinations. So we'll apply this to an exercise. You know what? I'll make a last note. Sorry, I'll make a last note on the intuition.
Could you just go up a tiny bit? Sorry for the definition of permutation. I just didn't go up.
Of course. So
All good.
just to give you a quick explanation, when we deal with events or sort of random experiments where we have equally likely outcomes, so each outcome has the same probability of happening, but the fact that there are a lot of many outcomes, it's sort of too difficult to count them one by one, then that's where we would use permutations and combinations. So the idea is that we'll use that when we have a huge amount of different possible outcomes that are all each likely possible to occur. And that's what we'll do in the next exercise. Is it good? Can I go down? Yeah, no?
Yeah, sorry. Yeah, sorry.
Yeah, no worries. Take it. What did I say? Take it. No worries. So intuition of combinations and permutations. We deal with permutations, combinations when one, we have many equally likely outcomes to count in a random experiment. All right, so let's see. No, that is not what I want to get. That is not what I want to get. This is what I want to get. All right. Up. All right, so yeah.
To make it a bit like bigger because we
Oh,
can see that much the text.
Yeah, my bad. Give me a sec.
Non mais en fait t'inquiète, hein, en vrai c'est bon.
C'est bon?
Ça
Désolé,
va.
genre c'est la deuxième fois que j'utilise un iPad.
En vrai ça va, c'est bon. T'inquiète.
Attends, tu sais quoi? Ouais, je vais juste mettre la même photo, mais non, c'est pas celle-là.
Ouais, non, mais t'embête pas, en vrai, si les gens like.
Can you guys see the read the whatever I put here? The little picture?
Yeah,
All right,
12 mutual.
Ouais, non, c'est bon.
There you go. All right, so we got sorry, just out of curiosity, because I think it's a voice I recognize. Is the French guy who just talked? Were you in 257, 250 last year by any chance? No answer.
Tu parles à moi?
Yeah. I was talking to you.
Ouais. Non, j'étais oui, j'étais déjà là l'année dernière, mais
I think I remembered you. I remembered you from my 250 class. Like your voice is reminiscent. Anyways, all right. So for the exercise, we have 12 managers that are being evaluated based on the historical performance over last year. So there are two types of managers. 6 are value managers, so we'll call them value managers, and the other 6 are growth managers. And on top of that, they're all ranked from 1 to 6. Well, and for the set of value managers, we'll rank them from 1 to 6, where 1 is the most experienced manager, and 6 is the least experienced manager. On the other hand, same thing for growth managers. We'll rank them 1 to 6, where 1 is the most valuable, the most experienced manager, and the 6 is the least experienced managers. So note that down quickly. All right, so we got 12 managers. So 2 groups, V1 to V6, and G1. G is for growth managers because 2 different types to G6, where 1 is the most experienced, 6 is the least experienced. All right. Also, one important note also, it says, so in the experiment, so they're going to be all 12 are ranked based on performance, probably a performance on the stock market or something like this. There's also one important assumption that is made. Assume that we have an efficient market, and that means that, which is equivalent to saying that each manager, regardless of experience, has the same probability of making the right decision. So equally probable of making good decision. And that that assumption, if I could say, is quite important. And that comes back to the intuition that I gave you guys here, right here, that we have many equally likely outcomes. And the fact that there's an efficient market, that means that nobody can predict with certain all the information. I think it says all the information is concentrated in the stock price. So the managers don't have any information whatsoever to use. So they're all equally probably likely of being first, second, third, up to 12. So first question. What is the probability that the top 3 managers in the ranking are value managers? So when dealing with exercises of permutations and combinations, it's fairly mechanical. The first thing you want to do is, first of all, are you dealing with combinations or permutations? Can anybody give me an answer by any chance? Does anybody?
Combinations.
Yeah, exactly.
All right. And can you explain why the combination?
Because like order matters.
So
And permutation.
Well, the order doesn't matter. We're asking if the top 3 managers are value managers. We don't really care if like V1 is the first or V1 is the third.
that's exactly right. So if I had V1, V2, V3, V3, V2, V1, these 2 are exactly the same in terms of the context of the question, because we don't care about the order. So these obviously are 2 different permutations, but they are considered as the same in the context of question, because we don't really care the ordering of the value managers. We just care that they're value managers. So we deal with combinations. To give if, for example, so the constraint here is that the 3 managers are value managers. Let's say if our constraint was that the first manager was the top 1 manager had subscript 6. If that was our condition, then that means that V6, V1, V4 is not the same as V1, V4, V6, because here this would satisfy this would satisfy our outcome or condition, whereas that would not satisfy our condition. Even though they're rearrangements, they're different. So in this case, we would use permutations, but here the rearrangement is actually the same. So we use combinations. So that's the first step, determining whether you use combinations or permutations. The second thing is calculating the probability. So the probability of I'll call it, sorry, just don't want to rewrite everything. Call it event E, just for the sake of facility. You always want to go about NA is equal to NA over N, where NA equals the number of outcomes that satisfy E. And on the other hand, N is number of possible outcomes in the experiment. And you know, this is fairly intuitive. Like it's just the basic definition of classical probability. You know, if I roll the dice, the probability of that being 1 is 1 over of getting a 1 is 1 over 6. That is the number of outcomes that satisfy the event of rolling 1, which is 1, and the number of possible outcomes, which is 6. So 1 over 6. Same thing here. So let's find N, which is a number of possible outcomes. We're dealing with combinations, and we want to know we're ranking 12 managers, and we're ranking the top 3. So we want to know how many ways can we combine, or how many different combinations of 3 managers can we do out of a set of 12 managers. So that would be 12 combination 3, which is equal to 12 factorial over 3 factorial n minus k, which is 9 factorial, which would be 220. All right. So we have n. Does everybody get why we got how we got n? If that's the case, move on to NA, which is number of outcomes satisfying the event, or satisfying E. And E is defined, if I can remind you, as the top 3 managers are ranked as value managers. So here, so again, we're dealing with combinations. So we want the top 3. So if we want the top 3, that means that we're going to get a set of 3 items. So k equals 3. And we want them to be all value managers. So we know that there are 6 value managers right here. So we want to see how many combinations of 3 value managers can we do out of a set of 6 value managers. So that would be 6 equals n, which is 3, 6, which is 20. So probability of the event E, that is the probability of the 3 value managers, the top 3 managers being ranked are value managers, equals NA over N, which is 20 over 220, which is, I'm not going to simplify that because 2 over 22, so which is 1 over 11. So that's for 1. 1 was the easier step of the question. I know that the year that midterm was done, I talked to John about it. He told me it was a complete disaster, especially because of the second one, the second question. So now let's assume we have the top 3 managers, all 12 are ranked, and we want to know what is the probability that the top 3 managers turn out to be ranked in order of experience, regardless of style. That is, the first subscript is strictly less than the second, which is strictly less than the third. So for those who, so 1, regardless of style, that means that V or G is not important. All right. And second thing is,
Matsur, we can't really hear you.
oh, can you guys hear me now?
Yeah, now it's good.
All right. Subscript 1 is smaller than subscript 2, and smaller than subscript 3. So to give you an example, if the first subscript right now. I'm going to illustrate point 1 at the same time. So it's V or G 1. So we got up V or G 3, V or G 5. So if that's the ranking, let's say, so regardless of style, we don't care if it's value of growth manager. If we have 1, 3, 5, then the first subscript is smaller than the second one, which is smaller than the third. So that would satisfy. On the other hand, if we have value 2, G 1, shit. So in this ranking right here, we don't care. It could be like G2, V1, or V6, or V2, G1, or G6. That would not satisfy the event that we're looking at, because the first subscript is actually bigger than the second one. So can anybody tell me now if we're dealing with permutations or combinations?
Permutation?
Yeah, and why is that?
Because you want a specific order, like you want to count every case of specific order and not necessarily random cases or random order.
Yeah, so specific order. So V1, V2, V3, definitely not the same as V3, V2, V1, because that would satisfy the event that first subscript is smaller than second, smaller than third, and this would not satisfy the event. So different orderings are considered different in that specific context. So we have permutations. That's what we're dealing with. Now, the second thing we want to know is, well, let's find n, all right? So n is the possible, so in our experiment, we're ranking the 12 managers, regardless of style. So what are the, and we want to know about the top 3. So since we're dealing with permutations, we want to know how many ways can we permutate a set of 3 elements, k equals 3, from our set of 12 managers or 12 items. So all the possible ways we can permutate the top 3 from the set of 12 is 3 permutation 12, which is, I'm going to save you the hassle, 9 factorial, which is,
Mathieu,
yeah.
since we don't care if it's V or G, shouldn't it be 6 out of 12? Because it could be.
No, it should be 3, because we're doing a ranking of 3 elements. So we're
Okay.
looking at the top ranking,
Okay.
and within that ranking, it can be V or G. It doesn't matter.
Okay.
So 3 actually corresponds to 3, which is equal to K, is actually correspond to the subsets we are making, and the subsets we are making are essentially the rankings, which is the top 3 ranking in that context. So we have n equals 1320, and now the weird part of the exercise, we got to count NA. So does anybody have an idea how we can go about counting the number of outcomes satisfying the subscript 1, subscript 2? Does anybody have an idea about how we could go about doing that?
I could try myself out, maybe.
Yeah.
Well, maybe I think we'd go like one position at a time. How many possible combinations there be for S1? And then after that, we'll deduce how many combinations for S2. And we'll all, after that, we'll multiply for the combinations for S1, the combinations for S2, and the combination for S3.
So you mean permutations?
Well, in this case, if we go like one at a time, couldn't we use combinations? I mean, I'm just thinking this off the top of my head.
I think you don't even need to use permutations or combinations. The sneaky way to think about this is to actually structure the number of outcome satisfying the event. It's structured in a very specific way, in a very clear way. So looking at each possible outcome, let's say the first subscript that ends up is a 4. The only way you can satisfy that event, satisfy the event that the first S1 smaller than S2 smaller than S3, is that we have 4, 5, 6. Fair enough? So there's only one way we can satisfy that. And then we want to see, given that we have subscript 4, 5, and 6, in how many ways can we permutate that with the value managers and the growth managers? So it's actually 2 to the power of 3 because we have I'm going to write it down because we have value managers or growth managers, and permutating for 3 elements gives you 2 to the power of 3, which is 8. But to make you visualize that, I can get like V4, V5, V6, right? At the same time, I can get V4, V5, G6, V4, G5, V6, G4, V5, V6, G4, G5, G6, G4, G5, V6, yeah, G4, V5, G6, and V4, G5, G6. 1, 2, 3, 4, 5, 6, 7, yeah. So which is equal to 8. So here what I've done is, if our first subscript was a 4, we can only satisfy the event with 4, 5, and 6. And we don't, it says in the exercise, well, in the beginning of the question, that V or G is not important. We don't care about the style of the manager. So we want to see in how many ways can we permutate V or G amongst the subscript 4, 5, and 6. And the answer is 2 to the power of 3, which would give you 8. So now,
How'd you get 2 to the power of 3? Like, what was the?
So, well, the intuition behind that is because you have you want to permutate V or G. Amongst 3 different subscripts, which would give you 2 elements to the power of 3, which is equal to 8. So here we actually fulfilled our we fulfilled our, if we have the first subscript is equal to 4, the only way that we can satisfy the event is 4, 5, 6. 4, 6, 5 won't work. So we kind of finished for this this first sort of first structure right here. And now we're just going to go down. If the first subscript is a 3, then a 2, then a 1. Now, if the first subscript is equal to a 3, then 3, 4, 5, that would satisfy the event. 3, 4, 6, that would satisfy the event. And 3, 5, 6, that would also satisfy the event. So essentially, if our first subscript in the experiment is a 3, then you want either the second and the third to be 4, 5, the second and third to be 4, 6, or the second and third to be 5 and 6. These are the only ways you can satisfy the event. These are the only ways you can satisfy the event if the first subscript is equal to 3. Now, the same method is used here. You have values or growth managers that you want to permutate amongst 3 subscripts. The fact that at the beginning I use the subscript 4, 5, and 6 is completely irrelevant. Like, it could have been 5, 6, 7, 20, 37, 2. the permutations, like I mean, the way you will permutate them. What matters is that you got two elements and you've permutated them amongst these three different subscripts. So that would give you 8. That will also give you 8. Also, I'll give you 8. So here we have 24 outcomes satisfying the event if the first subscript is actually 3. Moving on, if the first subscript is 2, then what satisfies the event is 2, 3, 4. 2, 3, 5. 2, 3, 6. 2, 4, 5. 2, 4, 6. 2, 5, 6. So these are all the list of subscripts that would satisfy the event if the first subscript is 2. And again, since we permutate V and G, V and G, since we permutate V and G from the 3 indices, I'm starting to make a lot of mistakes. I just want to also apologize for those who were there the first workshop. At the end, I started getting really tired, and I did a stupid mistake at the last exercise. So what I did was I wrote it down neatly, and I posted it on I'm sure most of you on the Econ 250, 257 messenger group. I posted the correct solution on the group, written out neatly. So sorry for that. I went a bit quickly and was a bit tired, which is not an excuse, but that was what was happening. So again, since we permutate V and G from the 3 indices, we got 8, so corresponding to that, plus 8, plus 8, plus 8, plus 8, plus 8, which is 2 to the power of 3 times 6, which is equal to 8 times 3, 6, 48 outcomes. So if the first subscript is a 2, then you have 48 outcomes satisfying the event. If their first subscript is 3, you have 24 outcomes satisfying the event. And if the first subscript is a 4, then you only have 8 outcomes satisfying the event. Last order of business. First subscript is equal to 1. That means you have 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6, 1, 3, 4, 1, 3, 5, 1, 3, 6, 1, 4, 5, 1, 4, 6, and 1, 5, 6. So when the first subscript is equal to 1, the number of so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 orderings of subscript that satisfy the event, which is the first subscript is smaller than the second one, which is smaller than the third one. There are 10 of them, and for each ordering that satisfies the event, you can permutate V or G in 8 different ways in such way. So that will give you 8 times 10, which is 80 outcomes. So, in conclusion, I'll call the event A. A is the event probability that first subscript and second, one and third subscript. And that will be equal to NA over N. We knew N was 1320 at the beginning, and N is equal to 8 plus 24 plus 48 plus 80. and that should give you symmetry. So country. So okay. So I can do 160 over 1320. So here we go. That's the answer to our question. Is everybody clear with that? I'm gonna post the notes, and in any case, I'm recording the lecture. So if you're confused with that, you can always go back to it. So can we move on
I
to
have so
yeah.
if we have more than 6 options, because wouldn't it would take so much time to like come up with all the subscripts, like, so like what would you do?
Sorry, can you repeat the question again?
Like what would happen if we have more than 6 options? Because then it'd be so difficult to come up with all the subscripts, I think.
Yeah, it would, but I think because I talked to John about that, and in that case, things would things would get really stingy. You wouldn't want to go about doing that. For this, because I talked to John about that exercise, and he told me that even when you had only 6 V's or G's, that was a lot for students to take. It wasn't the best exercise, but he said that was the best way of going about it.
Oh, okay.
Yeah.
I actually used combinations and I got the right answer. So, but I don't know if it's just because I don't see the logic behind it. But if I did, let's say, 2 to the power of 3 times 3c2 plus 2 to the power of 3 times 4c2 plus 2 to the power of 3 times 5c2. I think I forgot the first one as well. 2 to the power of 3 times 1. I actually ended up with the same answer. So
I see what you're saying. So 2 to the power of 3 times.
I couldn't explain why like I decided to do that, but I just did it.
2 to the power of 3 times. So 3 2. Oh, sorry. Wait. You know what? So you mean C2 3? You mean?
Yeah, sorry. I think because in French we say it the other way around, so I get mixed up.
Oh, okay. I see what you're saying. So 2 to the power of 3 times C 2 3 plus, and you got what? 2 to the power of 3 times after what you did.
C 4 on the top, 2 on the bottom. And there's also the first one that I forgot to say there, 2 to the power of 3 times 1. This would be for the first.
So for the one corresponding to 8 outcomes.
Yeah.
Okay. Yeah. And sorry, what was your calculation? 2 to the power of 3 times C?
5 2.
5 2. So your first one,
the first one is just 2 to the power of 3. Yeah, exactly.
Sorry. My bad. Sorry, let me. Yeah. I don't see. I definitely didn't think of that as a possibility. I definitely went about doing it that way. But if it works, then and you can find the logic behind that, that's good.
That's the problem. I can't see the logic behind it though.
Well, same. I'll have to take a look at it. I'll put that on the red. When I look over the notes, I'm going to make sure to take a look at that. Give it a little think. All right.
Thank you very much.
All right. I'll come back to you. I'll probably are most of you guys on the 250, 257 econ group chat by any chance? Or is anybody not in the group chat? Okay, well, I'll assume everybody is. I'll give a clear explanation to that when I take a look at it. But anyways, what time is it? Oh, it's already 6. All right. So now I'm gonna just do 2 more exercises before I go to the exercises. I just want to review very quickly for those who weren't there, conditional probability. Just yeah, just a few important notes. I'll take not more than 20 minutes on that. So if we have different events that happen successively in time, and these events and the outcomes of one of those events may depend on the outcome of the other events, then we use conditional probabilities. Give you an idea. Up, so I have an event E1, E2, another event A1, A2, A1, A2. You can define A2 equal to A1 bar, which is one. No, sorry, we're not dealing with probabilities, so I'm not going to write that. So essentially, the outcome of the event A1 might be dependent on E1. And the same thing, the outcome of A1 may be dependent on E2. The outcome of the event A2 may be dependent on E2 or E1 for that matter. So now we're sort of dealing with events in succession in time, and for that we'll use conditional probabilities. So let A and B be sets of events of a random experiment. Then the probability of A, so the bar means A given B. So the probability that A given that B has happened is equal to A intersection B over probability of B. So again, the probability of B that happens given that A has happened is equal to the probability of A intersection B, probability B. Note that here. Oops, my first mistake. The probability, so the probability at the top is always the intersection of the two events, and the probability at the bottom will be the one, of course, the probability of the set or the event which is at the right of the bar. So the event that has already happened essentially. And sorry, I'm just gonna. So if we have A, and this is, let's say, A bar, the complement of A that happens, B, B bar, B, B bar. That specific branch here is essentially the probability that you get B bar given that A bar has happened. That specific branch here is probability that B happens given that A bar has happened. Same here. Wait, sorry, I'm left-handed and lefties don't have it well on the iPad. But this is the probability of B given that A has happened. And here is probability of A given B has happened. Sorry, the opposite actually. The probability that B component happens given A has happened. Sorry. So I don't really like the tree in this case because it leads to the idea that in my mind, it kind of frames that A happens before B, which is not necessarily the case. We can look at probability. We can look at the probability that A happens given that B has happened. So definitely don't think of the trees, the tree branches as sort of time flying by, because it's not necessarily the case. Anyways, so that's our formula. We can rearrange and get the following. I did explain that in the first workshop, but since I'm sure some of you weren't there, I'm starting to have to pay attention in my writing. P of B times P of A. Yeah, you see, I have to make sure I'm not saying stupid stuff, which I currently am. There we go. In that case, probability A times probability B given A. So what I wrote here is just a rearrangement of 1 and 2, which leads to Bayes' theorem, which is probably A given B, equal probability of B given A times probability of A divided by the probability of B. Probability of B given A is equal to the probability of B times probability of A given B divided by the probability of A. So here, I just substituted for probability of A intersection B, which I got right here. So that's Bayes' theorem. That's conditional probability. A note on, I just want to make important note on intersections. I didn't make this clear last. Workshop, but it's actually a very important concept. So remember that we can represent events in a sort of in a sample space using a Venn diagram. So all these little, they're not boxes, but shapes. Let's say they all represent events. So let E1 to En sets of of an experiment, which is random, if I might add, and a set of. So omega is the sample space. So it's the set of all possible events that could happen within an experiment. And I'll denote A as this. That's quite important. Definitely will come up in your midterm. Well, like something to notice. The probability of A is actually going to be equal to the summation of the probability of A intersection EI for all I equals 1 to N. So we have in our sample space defined E1 to En experiments, and we have sets that correspond to events. So E1 to En are all events, and we also have an event A, and the probability of A is going to be equal to A intersect all the different events, E1 to En. So to illustrate, I'm going to illustrate this using a graph quickly. Let's say we have E1 bar, And then we have the event A complement, A complement. Then the probability of A is equal to the summation of I equals 1 to N of probability of A intersection EI. In that specific example, E1, EI just goes to 1. There's only E1, so it's summation. Oh, sorry. Actually, you know what? Just for the we know that E1 bar is not equal to E1, so we'll note E1 bar as equal to a second event, a second set corresponding to an event. So E2. So N goes to 2. So the probability of A is equal to probability A intersect E1 plus probability of A intersect E2. So there we go. So the probability of A is the probability that A and E2 happen, and A and E1 happen. So do you guys get that? Do you see what I'm sure it's fairly easy to see using this little graph. A is going to happen. It's A intersect all the other events that intersect A. So yeah, that was an important note. Before getting to the exercises, we're gonna talk about one last concept, which is really important as well, which is independence. Now, we'll keep it really short because in 257 D2, you're going to see independence. In 257 D2, you're going to study regression, and regression. When you study regression, it's really important that you understand the notion of independence because for various reasons. I'm not going to go into this because we have a lecture to finish. So let A and B be events. Sorry. Be sets corresponding to events of a random experiment. We got probability, sorry. We got A and B are independent. If and only if. So IFF is the same thing as if and only if. Probability of, wait, I'm going to write that in red because it's definitely going to come up during your midterm. Up, probability of A intersection B is equal to the probability of A times the probability of B, which is equivalent to saying that probability of A given B is equal to the probability of A, and the probability of of B given A is equal to the probability of B. So that second sort of derivation, the way you come about it is using this formula right there. You can just replace probability of A intersection B by probability of A times probability of B. Probability of B is on the bottom, so it cancels out. So you get probability of A given B is equal to the probability of A. And intuitively, it makes sense. If A is not dependent on if the probability that A happens is not dependent on B, then it doesn't matter that B happened because it won't affect the probability of that A happens. So probability of A is the same thing as the probability of A given that B happened. So that was an important note. All right. So now we'll go into the exercises. Actually, that one, the first one, yeah, that's the one. I actually pulled it out from my midterm, which was last year. C'est bon, t'arrives à lire maintenant? Voilà.
Mathieu?
Ouais, Yes,
Tu peux remonter juste un tout petit peu.
of course.
Oui, c'est bon. I'm good.
Just give me 2 seconds. I'm gonna get a glass of water. Getting thirsty. C'est bon? Is that good? Can we can I move down? Go down? All right. I'll take it as a yes. All right. I feel stupid because actually I didn't take a picture of the whole exercise, but to give you some context, so red and white. So we have the financial market, and we have regulators. We have regulators that regulate people, especially people who are specialized in the financial market and who give advice to their clients on whether to buy or sell stocks. So the regulators, they want to know essentially if the people who give advice on whether to buy or sell stocks are actually cheating, in the sense that we want to know if the person, if we have a person who knows about the financial market and who gives an advice to a client, is he does he have inside information on the stocks, or how the stocks are going to move up, or are they going to move down? We want to know that if they use that information, if they have that inside information to kind of cheat and tell to their clients, I know what's going on, so you should sell, or you should buy the stock. So in general, if the value of the stock is going to go down, then you want to sell everything, and if the value of the stock goes up, then you definitely want to buy some of that stock. So the regulators are here to try to determine whether the specialist is actually cheating and giving inside information to their clients before it's public, before it comes up to the public, which at that point will not be useful because the stocks would have changed in value. So we have the regulators that follow the woman's recommendation, the specialist, for 750 days. So we have 750 days, during which 75 days she called her clients to recommend selling the stock. So 75 days, she says to her clients, sell the stock. That means that the probability that the woman, the specialist, tells her clients to sell is equal to 75 over 750, which is 0.1. S equals sell stock recommendation. Oops. And general tip is as you're going through the exercise, it's always good to note as many, try to note all the information that you know or you can get. So we know then that the probability to that she recommends not to sell the stock is 1 minus P of S, which is 0.9. So 90% of the time she doesn't tell her clients to sell the stock. Moving on, 25 days on which she had recommended buying. So 25 days recommends to buy. So that gives that the B is the event, recommends to buy stock. Probability of B is equal to 25 over 750, which in that case would be 0.033. Regulators know the days on which negative and positive earnings developments were known to the insiders but not yet announced to the public. So on the days on which the broker said sell, 30% were days in which such negative information was known to insiders only. So I'm going to define a new event. Oh, negative information. Right. I minus is the event insiders knew about negative news. So it says that the probability, so on the days on which the broker said to sell to our clients, 30% of the days, 30% of the time, there was negative information that was already known to insiders. So the probability that she says to her clients to sell, given that insiders knew about the negative news, and we want to know if she actually had any contact with the insiders so she could extract the information. So that is equal to 0.3. So 30% of the time that she said to sell, the insiders knew that the stocks were going down in value. So over the 3-year period, there were 12 cases in which insiders had information earlier, on which 5 were related to negative earning news. And that was, I think, a very annoying part of the exercise. It's very subtle, but in each of these cases, insiders got the information 7 days ahead of the public. So that means that each time the insiders knew that there was negative information that was going to come out about the stocks, they actually knew that for 7 days. And since they knew 5 times that there were going to be negative earnings, each time lasting 7 days, then that means that there were 35 days where the insiders knew that negative information was going to come out. So that means that, switch to white, the probability that insiders knew about the negative news, there are 5 times where they knew about negative news, and each time they knew it for 7 days in advance. So they knew it for 35 days out of the whole sample space, which is 750 days. The insiders knew that there was negative news about the stocks. So yeah, here we have it. So now, first question, what is the probability that the brokers say sell when it's a day on which the insiders have negative news, negative information not available to the public? So, and it's not 30%, obviously. So here we're dealing with conditional probabilities. Reiterating the statement is, what is the probability that the broker said sell to her clients given that insiders knew about the negative information? So using the notation I had, what is the probability that the broker said sell given that insiders knew about the negative news? So this is conditional probability, basic stuff that I just enunciated to you just before. Here's the formula. Probably A given B is equal to probably A intersection B over probability of B. So that would be equal to probability of S intersect probability that she says sell and insiders knew about the negative news divided by the probability that the insiders knew about the negative news.
Excuse me, is that a plus sign on the I for A? Yeah.
Sorry, my handwriting is terrible.
But isn't that what you wrote 2 lines above? Or 0.
Sorry, let me just, yeah.
Is that supposed to be an intersection or?
No. It's actually the opposite. So on the days on which the broker said sell, 30% were days in which such negative information was known to insiders only. So it's actually the probability. I just reversed them accidentally.
Okay.
So it's actually reiterating the statement, it's the probability that insiders knew about the negative information, given that she sold, given that she said sell, is actually 0.3. Fair? Okay. So rearranging the statements, and it's basically the same thing as Bayes' theorem. We know that this is actually equal to, and for the person who just made the comment, the little mistake that I made, what we got 0.3 is actually going to be very useful. It's actually the same thing as this, and that's just the derivation to the Bayes theorem. So the probability that she says sells, given that the insiders knew about the information, is equal to the probability that insiders knew about the information, given that she said sell, times the probability that the broker said sell, over the probability that the insiders had negative news in advance. So we have that probability, which was given to us, which is 0.3, which says on the days of the broker said sell, 30% were days in which negative, yeah. So the 30% here, 30% here refers to the probability that negative information was known to the insiders, which is probability, which is probability that I minus given S is equal to 0.3. So this is equal now. So the probability that she said sells, given the insiders knew about the information in advance, is thus equal to 0.3 times. We know the probability of S, S being that she says sell. She said that you should sell 75 days out of 750 days. So she says the broker said to sell 0.1% of the time, divide the probability that investors knew in advance about the negative news, and they knew in advance about the negative news 5 times in total over time, and each time they knew it 7 days during a period of 7 days. So it's 35 over 750. And if you do the calculation, that should give you 0.64.
Could you just go up a tiny bit to the final probability?
Of course. So while you guys are writing, in essence, so you're gonna have exercises like this probably. So did he? I asked this last week. Did he say about anything about the midterm, about how it's gonna be conducted?
No,
Still nothing.
no. He just said a date, but that's it.
And do you know when the date is?
28th.
28th.
Let me
When is
check
that?
2 seconds.
Okay. So you have 1 month. All right. So
Yeah. I'm pretty sure he said it was 1 month from now, from yesterday.
okay.
He said that like past exams might not be as useful as like last year, because since it's not
Online.
in-house exam, the like way it's going to be done might be different.
Okay. So yeah, which is probably something I was expecting. I had a friend doing 257 D2. He missed the midterm and the final. He missed both midterms, so he had to take the supplemental exam. But since the supplemental exam was in August, which was during the COVID time, it was the same thing. Like the exercises were not the same as the practice ones or the ones that we had during the actual midterms. In any case, John's style of writing exams is very there's a clear pattern about how he writes exams, which is very correlated to the way he talks in class or writes his textbook. So still getting that practice is still very useful. Anyways, question B. And maybe you'll have to do data analysis. I don't know if it's at home and you guys have to do data analysis. Well, it will probably be maybe some data analysis and some probability exercises. We'll see. Anyways, for question B, we're asked, what is the probability that we both, and that's important, that we both have a sell recommendation and negative information to insiders only? When we're talking about both, we're dealing with intersections. So for those who don't remember, intersections is the probability that A intersect B is the probability that A and B happen at the same time. So here we want to look at the probability that the broker says sell, and at the same time insiders knew about negative information. So you want to know about the probability that the broker says sells, and at the same time insiders knew about the negative information. And this is fairly easy. We just answered this right above for those who can see. It's actually right there. Because when we wanted to determine this probability, we needed this, which is equal to this, which I wrote right here. So in essence, it is equal to probability of I bar given S times probability of S. This is just rewriting conditional probabilities, which gives you 0.3 times 0.1, which is 0.03. There you go. So the probability that she says sell and at the same time insiders knew about the information was equal to 0.03. So next question. What condition on the quantities you calculated or been given should hold if the broker doesn't know or use the negative information? So there's definitely no calculations here. Can anybody state to me, or does anybody have an idea what should be the conditions to state that she's innocent?
It would be independence of the events.
Yeah, so we're looking at the fact that there's an independence between the fact that she says sell to the client and at the same time there's independence between that and the event that the insiders knew about the negative news in advance. And the idea is that if they're actually dependent, if every time insiders knew that you had to sell the stock, if every time they knew that, then the broker said, all right, to my client, you should now sell. Well, that becomes very suspicious. And that would mean that both events are dependent, and that maybe the broker is cheating and knows about the information in advance from the insiders. So we want to know if event S sell and insiders knew about the negative information are independent. Are they asking us to calculate that probability? What condition? Should this hold in population, sample, or both? What the hell does he mean by that? Explain, including what you mean by population here. I have no idea what he's talking about, but if you guys have any idea about what he's talking about, go ahead, but speak up, but didn't read that and don't think it's very important. So anyways, question E, or D, I don't remember, just asks us to formulate that numerically. So how can we see if that's the case? You want to see, obviously, if P of S intersect I minus is equal to P of S times P of I minus. Also, you guys haven't studied hypothesis testing. So in hypothesis testing, we would actually make that hypothesis and we look at the data and we have certain margins of error. And So we have a margin of error when it comes to that. When we do hypothesis testing, here there's literally no margin of error. So I mean, the best way you would do that is using hypothesis testing, which you haven't learned yet. So you want actually to know if these are more or less equal. You don't want to in reality you want to see if they're more or less independent. You don't want to see if they're strictly independent. If there is some association between both, as long as it's very small, then hypothesis testing will still say that that they're independent more or less. So this is equal to 0.03. And on the other hand, we have P of S times P of I bar. So probability that she says sells times the probability that insiders knew about the information. That was 35 out of 750. Which is 35 out of 7,500. And if you look at that, you get, so you get 0.03, which is definitely, you get probability that S intersect I bar is definitely not the same as probability S times probability of I bar, which leads us to conclude that she's cheating. Or that it looks bad, that this is not looking good for her. So the events are not independent, definitely not independent. All right, so that's that. So it's been 1 hour and 15 minutes since I've started. I think I have space for one last small exercise, and then we'll wrap it up. All right. I just want to see how many people are in this Zoom call. 17 people. Just curious to see. All right. I'm sorry if my handwriting is not that good. I'll post everything on the group chat on the ESA Facebook page, which I did for the last week's lecture as well already. But in any case, it's recorded. So if there's something you want to see. And also, last week I did a stupid mistake on the last exercise. So if there's any inconsistency, don't hesitate to send me a message on Facebook. I'm on well, you guys know where to find me. All right, so last part. Wait, you know what? Great. That should be readable. All right, so we're looking at a group of economists to see if a program to support entrepreneurship in a developing country works. So the program offers small loans to the entrepreneurs. On top of that, there's a training program in running a business, but participation is optional. It's an extremely important point. We got a training program, which is optional. The programs have been in place for some years, and there's substantial data about whether or not business has survived, and whether the business has completed the program, how large the startup loan was, has the person given capital to support her business, and whether the business. That's about it. Not very important stuff. Now we want to look at the numbers. So you can only fail or survive your business. So let's say F is the event business fails, and F bar, since it's binary, business does not fail. No, the probability that a business fails is 25%, which is that, and the probability thus that a business does not fail is 75%, which is 1 minus 0.25. On top of that, and the probability that an entrepreneur takes a training course is 0.6%. So if C is the event, the entrepreneur takes a training course, and that means the probability of C, the proportion of people who take the course is 0.6, so 60%. So the probability that they don't take the course is 0.4 in that case. Additionally, 10% both take the training course and end up failing. So probability of failure. And so when we talk about both or and, like these are keywords for intersection in general. So the probability that you fail and at the same time you took the course is equal to 0.1. So 10% of people fail and take the course at the same time. Well, both take the course and fail. And the probability that an entrepreneur contributes his or her own capital is 40%. So I'm going to define the event K as capital how did they say this? Contribute. That was the word I was missing. Contributes capital. And at the same time, K bar does not contribute capital. So probability that you contribute capital is 0.6? 0.4, my bad. So the probability that he does not give capital, 0.6. There we go. And of those who do contribute capital, the probability that the business fails, the probability that the business fails given that the individual has contributed some capital is equal to 20%. All right, so definitely a lot of information to extract here. What's easier about that exercise is that the information is direct, whereas for the other one, all the information, well, all the probabilities were set as a function of time. So you had to divide everything by the number of days, and an event might have happened multiple days. So it was trickier to extract the probabilities and actually the relevant events in the experiment. Here it's more trivial. So anyways, find the probability that a business fails if the entrepreneur took the course and in second part did not take the training course. So probability that entrepreneurs fails given that he's taking the course, probably F intersects C over probability of C. That's basic conditional probability. And the probability of C is equal to 0.6. And on the other hand, probability that he fails and takes the course is 0.1, which is 1/6. On the other hand, we want to know what's the probability that the entrepreneur fails and did not take the course. Getting used to that more. That's good. Probability of F intersect
Your audio cut out.
Oh, I thought I was the only one not hearing anything.
No, I thought my Zoom was crashing.
Oh. Can you guys hear me by any chance?
Matthew,
Yeah.
everyone left.
Oh, everyone left?
Yeah,
Oh,
I
okay,
just
okay.
stayed on because I didn't know what that would do to the recording.
Oh,
And-
okay, perfect.
But
Okay,
yeah, everyone, literally everyone left. So
Okay. When did they leave?
anywhere from 10 minutes ago to 5
Oh,
minutes
okay,
ago.
okay. All right, fair enough. Okay, well,
Okay,
I think we're
but
done.
thanks anyway.
Yeah, no worries. I hope this helped. Pretty long
definitely, yeah.
session. But all right, take care.
All right, you too.